Here we go. It says, after the release of radioactive material in the atmosphere from a nuclear power plant at Chernobyl in 1986, the hay in Austria was contaminated by iodine 131. That 131 is just a number describing the iodine. Don't let that 131 bother you here. Which is known to have a half-life of 8 days. If it is safe to feed the hay to cows when 10% of the iodine remains, how long does it take how long do the farmers need to wait to feed them the hay? Okay, so here's Chernobyl. Here's Austria. It's pretty far apart. I would say at least 1,000 miles. We're getting some radioactive hay. We need to figure out what's going on. So when we read this problem, we see half-life of 8 days. So when we see half-life, we know the best way to attack this problem is to cut my paper in half. First thing we're going to go through is understanding half-life. Y equals AE KT. Jack, what's something I can plug into that formula? 1 and 2. Good. It's half-life. Okay. So Jack said if he started with 2, now it doesn't matter what he started with. Whatever number he's going to put there for the initial amount, he's going to cut it in half. Okay. So 2 and 1, 150, 10 and 5. It doesn't matter because the very first step you're going to divide and you're going to get 1/2. E. The first time through, I'm always going to find my growth rate. I need to figure out what my K is going to be. In this case, it should be a decay rate. And T is going to stand for time. Bless you. In this case, what is T going to be for us? 8 days. Okay, there's my setup. Now I'm going to solve. Sam M, what am I going to do? Divide by 2, divide by 2. So I get 1/2 equals e to the 8k. Then what? ln and divide by 8. Good. So natural log of 1/2 divided by 8. That is going to tell me my k value. So I had a student yesterday that was like, hey, can I always, if I'm doing half-life, just take natural log of 0.5 and divide by the half-life? Sure. It's what you're going to do. It doesn't matter if you want to come up with that formula and say and remember it. Sure. Or you can just do the problem. I get that. K is equal to negative 0.0866. Does it make sense that it's negative? Yep, because the iodine is going away, or at least hopefully. There's our first formula. Now we're going to plug back in. Y equals AE KT. Kara, what can I plug in this time? We can plug in K. Yep, we can take that K and plug it in. What else? Huh? Not this time, because that was our half-life. We're trying to figure out how long. So that's the ultimate goal here, is try to figure out how long. We need to come up with some amount, some starting amount. What starting amount would be an easy number to use here, Kara? Yeah, that's fine. 1 and 0.1, or you could say, hey, I start with 10 and I'm going to do 10%. It'd be 1. Either way, again, when I divide, it's going to get me 0.1 because I want to get 10%. That's the ultimate goal here, is to get 10%. So we got that set up. E, we know what our K is. It's going to be that negative 0.086 number and divide by 10, or multiply by 10. T, whatever. Divide by 10, divide by 10. Natural log, natural log. So natural log of 1/10, and I'm going to divide it by K, and that's going to tell me the time. Natural log of 10, divide by my K. So after 8 days, there'd be 50%. After 16 days, there'd be 25%. After 24 days, there'd be 12.5%. I'm cutting it in half. And so 24 days, I was at 12.5%. So 26 days. Oh, I have natural log of 10 instead of 1/10. They got everything the same. It was just 26.575. Okay. 26 days. That makes sense in terms of what we set up. 26.575 days is going to be my answer. How do you think those cows did? Bad. Those cows are not real happy. Okay. Understand that's Chernobyl. So anything in this radius, basically the cows are going to die. Okay. They can't eat the iodine. Or the iodine would be iodine poisoning. That'd be bad. Okay. And that was 26 days. Like, I'm sure if you went out a little bit longer, it'd probably be like they had to wait at least 10 days. And probably cows didn't really like that either. Okay. Pretty interesting. Anybody seen the Chernobyl documentary on HBO. One person, yeah. Thank you. It was so good. It's so good. Check it out. Very interesting. It is very interesting. I agree. It is. It's a crazy amount of stuff going on there. Check it out. That's my recommended viewing for you. It's a good learning experience about Chernobyl. All right, let's finish up notes from yesterday. Similar concepts. We're learning two new setups here, but for the most part, it's going to be pretty much the same. So today we are talking about Newton's law of cooling. It's kind of a crazy formula. It's a lot like Halflife. Okay, what Newton's law of cooling is a formula that's going to be able to tell us how fast does something cool based on what temperature the thing is and what temperature is around it. Okay, so basically, how do those two things go together? So if you took a pot roast out of the oven and you put it in the refrigerator, how long would it take to get to 100 degrees? Okay, that kind of thing. Okay, we'll explain it here in a second. So the temperature of a heated object at a given time can be modeled by this equation. Okay, T. So U of T is going to be basically the ending temperature of this thing. T is the constant temperature of the surrounding medium. So what is the temperature in the room? What is the temperature in the whole refrigerator? That is T. U sub 0 is the initial temperature of the heated object. All right, so when I took the casserole out of the oven, it was at 190 degrees. That was the initial temperature. Right when we started, it was 190. Okay, and K is going to be a negative constant. Why do you think it's going to be negative? It's cooling. The temperature is getting less and less. It's a decaying value. All right, T is time. Let's do it. Your Starbucks barista serves you coffee at 185 degrees in a restaurant that is set to 68 degrees. After 2 minutes, the coffee is 163. How long will you have to wait if you prefer your drink to be about 140 degrees? All right. So like Half-Life, we need to first start off by solving for K. All right. We need to figure out what is our rate of change. Once I figure that out, I can do everything else. So again, it's like splitting our paper in half. And the first time through, we are going to plug in information that's going to allow me to solve for my K value. So basically, if I want to do that, I need to plug in something that I know. I need to plug in a time that I know to allow me to solve for K. So thoughts, what's something I can plug in here? 2. What am I plugging 2 in for? Minutes. Okay. 2 minutes. What else can I plug in? T stands for the initial temperature of the surrounding medium. What is the temperature of the surrounding medium? 68. It is 68 degrees in the restaurant. So this is 68 and this is 68. U sub 0 is the initial temperature of my coffee. What am I going to plug in for that? 185 is my initial. 185 minus 68. And then U sub T is going to be my temperature after the time. What is U sub T going to be the first time through? That is going to be 163 because I know after 2 minutes, my coffee is going to be 163 degrees. Go. Solve it with your neighbor. Figure out what K is. Here we go. If I were to solve this thing, if I'm solving here, Ella, what'd you do first? Subtracted 68. So then I've got, well, I'm not good at math. It's not my strong suit. All right, 95. My bad. 95 equals 185 minus 68. That's going to be 117. E to the 2K. Then what'd you do? Divide by 117. Divide by 117. Then you did what? Natural log. Natural log. And then to finish this thing, you divided by 2 to get K by itself. So in her calculator, she is taking the natural log of 95 divided by 117. Close those parentheses and divide all of that by 2. That's going to get me my K value. K is equal to negative 0.104. Again, I'm not really rounding it. I'm just writing it down on my paper. Does it make sense that it's negative? Yeah, because I'm getting cooler. Once I find my K, then I can go ahead and plug back into this equation. So this time through, same concept, but it's not exactly the same. It's still 68 degrees in the restaurant. It still started off at 185 degrees. It's still 68 degrees in the restaurant. I know what my K is. This time through, I'm trying to figure out how long. So I'm searching for T. I know what my K is. I found it. So the only thing that I have left then is I need to plug in U of T. What is my temperature going to be this time through? This time through, it is what I'm trying to reach, which is 140 degrees. Okay, I'm trying to get to 140 degrees. That's the ultimate temperature here. That's the goal. So then we're just going to solve. Subtract 68 on both sides. And it looks almost identical to the last solve we did. Okay, I'm going to divide by 117. I'm going to take the natural log. And then I would divide that by my K value that I just found in my calculator. So in my calculator, I'm doing natural log of 72 divided by 117. And I'm going to divide that all by my K value that I just found. My time is 4.662 4.662 minutes. Questions there? Yes, ma'am.
So how can you tell like the initial temperature isn't 163? Like how long?
You could do it with 163, then you would just have to add 2 to it.
But like, how do I know that's not what the question's asking? Like it's like to me the question looks like it's asking how much longer do you have? Like from 163.
Well, you would get 2.662.
But would that be wrong?
Yeah.
But like how the wording of the question, like it just looks like.
How long must you wait if you prefer to? Well, if you said 2.663, would I really count it wrong? Probably not. It's okay. Don't get into semantics about the question. On an SAT question or an AP question, they're very specific. This is not to that level, so it might be confusing overall. They would probably specify how long total would you have to wait, or how much longer after the 2 minutes would you have to wait. My guess is that every time it's going to always refer to that full time. I understand the confusion. Don't let that be bothersome. Questions here? All right, go to the backside. Backside, we're changing gears here a little bit, but still the same concept. Okay, this looks hard. It's not hard. All right, logistical models. A logistical model can describe situations where the growth or decay of a dependent variable is limited. Okay, we have a new model, P of T equals C over 1 plus A of E minus BT. Here is a description for you. Imagine you have a fairly small island, okay, 2 square miles. It's got monkeys on that island, okay? That monkey island has no natural predators. There are no monkey eating sharks. Shark eating monkeys would be weird. All right. There's nothing that's killing the monkeys off as a predator, okay? Will the monkeys grow unbounded? Will they continue to grow forever and ever and ever and ever and ever? No, because eventually you're going to have an island where you just have monkeys stacked on top of each other. And that's really weird. Eventually there becomes a limiting factor to that. Everybody understand what's happening? So your rate of monkeys is going to grow for a little bit, but eventually they're going to be mad at each other. Okay? They're not going to hang out anymore. They're going to stay by themselves and go hungry or whatever it else is, but it's going to flatten out. Okay? And there's going to be a certain limiting factor that you can't have any more monkeys than this. That's what's happening with these equations, okay? These are logistical models, okay? That number that limits you, okay, the most monkeys that you're going to have, that eventually it's going to flatten out, it's called the carrying capacity, okay? That's this number right here, the carrying capacity. Whatever's on top, that's what's going to limit us, okay? There's going to be a horizontal asymptote at that carrying capacity that we're going to really approach, but we're never going to go over. Two different things could happen with it. Okay, so here are some properties of. you have two horizontal asymptotes, y equals 0 and y equals c. We're never going to get less than 0 when we talk about logistic models. Okay? They could either increase like this and get closer and closer to the carrying capacity, or it could start at the carrying capacity and get closer and closer to 0. We are going to do the first one more often, okay, where we're going to get closer and closer to 0. B represents your growth rate, okay? We are going to have this place on this graph called an inflection point. That spot right there is the inflection point. That spot right there is the inflection point. Talk with your neighbor and describe what does that inflection point, what is happening on the graph at that inflection point. Talk with your neighbor for a second. Come up with a description. All right. We have an inflection point. Anybody have a good description as to what is happening at that inflection point? What you got for us, Aaron?
It had like a positive acceleration and then it went negative.
I definitely would agree with that. We're talking acceleration there. She said positive acceleration, negative acceleration. Most of you probably don't necessarily understand that. That's something we get into calculus, and so it's a little bit different. I would definitely say it's the halfway point between the two asymptote lines. So that would be one thing the inflection point is. What's happening here is think about growth. At this point, the monkeys are growing at a faster and faster rate. Okay, they're becoming more and more monkeys. Here, there's still more and more monkeys, but they're not growing as fast. Okay, she talked about positive acceleration, negative acceleration. We're getting more and more and more. Here, it's getting more, but it's not going at fast of a rate. Okay, so the rate is increasing or the rate is decreasing. That's what's happening here. To make this description, we're going to use something called concavity. Okay, so for me, the best way to represent concavity is put your hand on the graph and let your hand model the graph. Okay, so if I were to model this graph right here at the beginning, I would use my hand palm up. Okay, and my hand would go palm up all the way until that inflection point. And then what would happen right about there? To be natural, I would flip my hand over. Okay, and then it would face down. When your hand is facing up, when it is increasing, we call that concave up, like a cup. Your hand is up like a cup, up like a cup, up like a cup. And then when we get to that inflection point, we flip. Our hand goes the other way. Now I'm concave down like a frown. Down like a frown, down like a frown. That's real calculus language. Concave up like a cup, it's bending upwards. Concave down like a frown, it's bending downwards. Okay, up like a cup, down like a frown. The inflection point is the place where you change concavity from up like a cup to down like a frown. Go with that. I won't make you memorize this formula. I would give you that formula on a test or quiz if I were to ask you to use it. All right, here we go. Let's see what's going on here. According to a survey, the percentage of companies reporting usage of Microsoft Word T years since 1984 is given by this. So P of T represents the percentage of businesses that use Microsoft Word. What is the growth rate in the percentage of Microsoft Word users? So that's not a calculation. It's just looking at the formula. What is the growth rate here? Yeah. I think growth rate is always the thing in the exponent with the t. Oh, but it's got a negative sign. Do you think Microsoft Word companies are getting less? Not in 1984, it wasn't. Okay. The answer is 79.9%. That's the growth rate. Anybody can explain why it's negative? Because it's in the denominator. Okay. It's in the denominator. They could put that in the numerator, but if they put that in the numerator, then it gets a little bit ugly with the carrying capacity. So we put it in the denominator to kind of keep those two things separate. So it's negative. The B is just the number itself without the negative sign. Using a graphing utility to graph the function, what was the percentage of Microsoft Word users in 1990? Cool. So let's type that into my calculator. Go to y equals alpha F1. We use the fraction button. We type that thing in. Take a second, type that in. We type that thing in. Let's go to window. So here's what I'm going to do with my window. X min, I just left it at -10. X max, I made it 10. Nothing needs to change there. The thing I did change was my Y minimum. I made it 0 because this is percentage. I don't care about less than 0. And my Y max is going to be 100 because I don't care more than 100%. And then I changed my Y scale because I hate when there's just a solid black line. I like to make them have hash marks. Everybody go with that? We type that in. So 0 to 100 because I'm doing percentages. Let's graph it. Oh, there we go. I got a nice little logistical line. Tell me now when you think I've reached the inflection point. Yeah, right about there. In the middle. It's the in between place when I'm up like a cup to down like a frown. It's somewhere in there. All right, but cool. We got that. The question is, what was the percentage of users in 1990? What am I going to do to figure out the percentage of users in 1990? Make my X, make my T equal to what? I wouldn't want to plug in 90. Why do I want to be 6 here? It's since 1984. So since 84. 84 was year 0. So 90 would be year 6. So all I want to do is plug in 6. So to do that, there's lots of different ways. I'll do it this way. Second, calculate the value, which is number 1. That's going to let me plug in any X value I want. In this case, I want to plug in X is equal to 6. I hit enter. Boom, right there, it's 97.316%. That's a lot of people using Microsoft Word in 1990. I don't know if that was true or not, but if they put it, I'm guessing so, 97%. During what year did the percentage of Microsoft users reach 90%? What can I do to figure out when we reach 90%? Y equals 90, because we want to know when it's 90%. 90% is a Y value here. So we're going to graph 90. There's 90 right there. We're going to find out where they intersect. So I'm going to go second, calculate. The intersect. I want to know when they cross. I'm going to move this cursor to where I think they cross. I'm going to hit enter. Second curve. I'm going to hit enter again. Guess I'm going to hit enter again. 4.163. So during what year is that happening if it's 4.163? Yeah, that's 88. It's because year 4 would be the start of 1988. So it's somewhere during the year 1988 on that one. Last one, talk with your neighbor for a second. Explain what the numerator given in this model represents. What does that 99.744 represent? Does it imply and does it make sense? Talk with your neighbor for a second. Come up with an answer for that. 99.744, that number on top represents the what? That's the maximum. What's the word we're using in these logistical models? That is the carrying capacity, or in other words, the most we can have in this situation, which probably in the early 2000s made sense. 99.744 was probably the most percent that a business could have because it's almost 100. I would bet almost everyone was using Microsoft Word. There's probably like one person out there using Word perfect. Okay. Do you think right now that it's still 99.744%? No, if I ran a business, I wouldn't use it. Why not? Google's free. Free is better. Okay. I'm all about free. I'm sure Microsoft Word, I still use Word all the time. I made this document in Word. But if I were running my own business, I wouldn't use it. I would use Google Docs all the time and be able to share stuff easier. Questions on something we learned? One